Okay, thank you for giving me the possibility to talk about this baryogenesis model. I was asked to talk about this, and I must admit I'm not particularly proud of this model. so I think at first I want to say what we thought to do, and then I will tell you what we did, and you will realize that there is a huge divergence. But the idea was to, maybe it's a workshop, so I can say some words. So the idea is that there are models where the Higgs is composite, and maybe if the fundamental dynamic is similar to QCD, maybe you have a phase transition density scale, no? So in QCD, if you have enough flavor, the phase transition can be first order. So then, if this is the case, I'm not positive that composite Higgs is really like QCD, but maybe in a toy model, you can have a first order phase transition that also generates something that resembles the Higgs, okay? And when you have a first order phase transition, you can use it to generate some particle asymmetry, okay? Especially if the condensate carries some quantum number, okay? Of let's say, of a U1x. We tried, but I think, well, I'm speaking for myself. I realized I didn't know anything about baryogenesis. So we disregard this possibility, maybe because it was too difficult for us. And then we try to, see if something like this can happen in the standard model in a very simplified picture, okay? So in the standard model, you can write something similar at the renormalizable level for the right-handed neutrino, okay? So maybe the mass of the right-handed neutrino is generated by some first-order phase transition, okay? The VEV or of a scalar field, which carry Lepton number, okay? And eventually, we will depart from the scientific scale because the model is quite restricted. Okay, right-handed neutrino with a given mass. Okay, and we will be forced to go to the high scale. Now, okay, no, I don't know. This is what we did. So maybe I will try to discuss a few aspects, and maybe if there is something to it, one can possibly try to modify the model and get something better, okay? Okay, so first of all,
negative introduction, whatever you do is look amazing.
you think so? well, you can always judge, you know? So, okay, so in the standard model, you have baryon number violating processes, now in the sense that this current is not conserved, and there are field configuration that break B plus L conserving B minus L, for example, with 9 quarks and 3 leptons. Okay, processes like this. These are the Sphaleron processes that have a rate which is alpha weak to the fifth t to the fourth. Okay, so given the fact that they conserve B minus L and they set to 0 B plus L, if you are able to generate a lepton asymmetry in the early universe, the standard model will take care of that, in the sense that you have two equations, like B minus L is constant, maybe it's constant to the initial lepton asymmetry, minus. And if these processes are fast, B plus L will be equal to 0, so eventually you have a final baryon asymmetry, which is what? Yeah, absolutely. Yeah, if you want the number, I think is Minus. Well, unfortunately, I have it. Yeah, it's an order 1 number anyway. 28 minus 79. I think is Harvey Turner. Okay, and and this mechanism is exploited in electroweak baryogenesis, for example. And the model that I will discuss is a deviation from electroweak baryogenesis in the sense I'm using the same ideas at a different scale and with different processes. So maybe I will tell a few words about electroweak baryogenesis. So basically, you need bubbles. You need a first order phase transition with bubbles that carry that breaks electroweak symmetry. Now, the fact that you have a profile in V, and also is very important, a profile in the phase, these two ingredients are enough to generate an asymmetry at the bubble wall. Okay, so we have this bubble of V different from 0 that are expanding in the region around the bubble wall where you have a gradient for delta Z, theta Z. You generate an asymmetry in chiral charge, okay? This background breaks left-right symmetry, chiral symmetry, so you are able to generate an asymmetry in, let's say, in the abundance of the left-handed top and right-handed top, for example, or quark in the standard model, or in in the stops if you have the supersymmetric version of electroweak baryogenesis. Now, this is the first step. The second step is to use the Sphaleron, because notice that the Sphaleron only acts on the left-handed fields. Okay, so given the fact that you have an asymmetry in the left baryon number and in the right baryon number, processing this asymmetry with the Sphaleron will give a net contribution to baryon number. Okay, so the Sphaleron generate a net baryon asymmetry. Now, the very nice property of electroweak baryogenesis is the fact that the Sphaleron have this rate outside the bubble, but inside the bubble they go immediately out of equilibrium, because now if the rate here is alpha weak to the 5th, t to the 4th, now here the rate is suppressed by non-perturbative contribution, okay? And this number is very large, provided that V over T is order 1. And this parameter is what people usually discuss the most in model where you have where you try to modify the standard model where you don't have this property. The fact that you have a first order first transition, so you can add new physics to get to this point. Okay, so this is the idea. So there are basically 2 steps, and you need some CP violation at the bubble wall. Now, can we do the same? Yes, of course. The crucial difference will be what we do here, in the sense that we don't generate an asymmetry in chirality, and the ugly part of the model is that we don't have a nice non-perturbative process that will be out of equilibrium inside the bubble, but we will have a perturbative process. So then the washout will play a major role in ruining the model, okay? But anyway, it is what it is. So oops. Okay. I'm going to slow. So the idea is to generate a delta L from the fact that sorry, that you have Majorana neutrino masses from a first order phase transition. Okay, so the model is defined a standard model. Yeah, a standard model with a Handy neutrino, with interaction that preserve lepton number. Let me add some scalar field. I mean, this model is very unnatural, so this scale will be high. I'm not really worried about that. Maybe there are nicer models, but I'm focusing on the mechanism. Okay, so this preserve a lepton number, and there will be corrections to this Lagrangian that depend on the fact that at some point, when the scalar field carrying the lepton number will get a wave, you will have, again, expanding bubbles which will carry lepton number, okay? So let me add let's say, one interaction which will be z-dependent and will be a proxy for the fact that this guy will get a wave that depends on z, okay? This interaction breaks lepton number. Good, so I want to get rid of this guy, so I can do a free redefinition, and I will get a Lagrangian like this. A real mass for the Majorana neutrino plus a derivative interaction of, let's say, these are like some background field, theta depend on z, times this is a Weil spinor, so it's a left-handed current for the Majorana neutrino, and this approximation is valid outside the bubble. I mean, I can talk about a left-handed Majorana neutrino because it's massless at high scale and close to the wall. Okay, inside I will not distinguish about among N and bar. Okay, inside I will talk about just a Majorana neutrino. Yes.
You don't have both the KS and N term and the MZ term, but MZ is just the web.
Yeah. So I'm writing the lepton number preserving interaction, and now when S will get a wave, I will develop this z-dependent interaction close to the bubble wall. Okay.
What is the scale of it? So this is the transition that you're talking about is the prolific transition.
No.
You're talking about some other.
No, I mean,
That has nothing to
I was hoping that the final Baryogenesis symmetry will not depend so strongly on the CISO scale, but because of the washout, because it's perturbative process, at the end I will be forced to set to the high scale. That's the unfortunate part. Okay, so anyway, to break CP, you get a profile for theta, okay, from this Lagrange. So the ingredient again is similar. You get theta prime different from 0. Okay, these two ingredients. Good. So the idea is to generate a delta n asymmetry like a chiral asymmetry in the electroweak baryogenesis case at the wall. And I will not follow chirality. I will follow the helicity of the Majorana neutrino, because outside I have the neutrino with the, let's say, helicity plus and the antineutrino with helicity minus. Okay, so I will follow the helicity. In principle, I could follow the spin, but this is more simplified. So,
But you have, in addition to this, the natural decays of N, the leptogenesis like.
absolutely. Okay, that's true. So inside, you can have thermal leptogenesis, no? But thermal leptogenesis depends a bit on the spectrum of the Handy neutrino, no? Because the efficiency depends on the splitting between the N1, N2, and 3. In this case, provided that I'm able to get theta prime, the Handy neutrino sector is yeah. Okay. So yeah, it can. This could be a subleading contribution to thermal leptogenesis if it happens to be a first-order phase transition. Absolutely. Okay. So I will try to generate a delta n at the wall, and then I will try to redistribute it to delta L via the Howard interaction. Now, since this coupling needs to be, this interaction needs to be in equilibrium, lambda n needs to be large, so the CISO scale goes up. Okay, that's the problem. Okay, so first generate delta n, then redistribute the asymmetry to the lepton, and then avoid washout. Okay. So there are 3 steps, and I don't know. Maybe I will comment about them.
If you go to the 3-flavor case,
yeah,
the leptons, I thought you could take very large imaginary parts for the Yukawa coupling without screwing up the neutrino masses. Did you look into that?
For thermal leptogenesis, you mean, or
no, for well, even for the it's actually necessary for low-scale leptogenesis when you do this resonant.
No, actually, I didn't look much into Majorana sector. Okay. Yeah. I mean, it's the same like in the standard model. So in the standard model, you need a phase gradient which depends on z, which is very difficult to achieve. So you go to MSSM or to X-level model where theta prime is proportional to tangent beta prime. No. So even in the MSSM is a property of the scalar sector more than the CP phases in the interactions. No? So maybe I didn't say, but in 2x double model, theta prime is proportional to beta prime. So you see all this formula proportional to beta prime. The fact is that you need to source a chiral asymmetry.
Right, but here your case is not proportional to beta.
Well, I mean, again, if you really want to have this property, probably you need.
I want to argue the basic picture. So here the phase transition is triggered by this.
Right.
This scalar which gives the Majorana mass.
Right.
Neutrino, right.
Yes.
And simultaneously, this breaking has the CP violating lab, which triggers
yeah.
chemical potential splitting.
Absolutely. Good. Okay, so the computation of the source, I think, is to me, was the most difficult part, and we did some very naive estimate. There are, I think, 2 methods: CPT formalism and some semi-classical force approach. I think this was pioneered by Riotto. This is probably Klein and collaborators. I will do the ancestor of CPT formalism, which is a paper by you and Nelson. I think it's 1994, something like that, which is very interesting. And I think the results have been shown to be very in agreement, okay, with this formula. Not with this. There is some wall thickness dependence that is not matched. Okay, so so the source of n number is proportional to the difference between the transmission and reflection, say transmission probability of a neutrino and an anti-neutrino. Okay, so this is like the propagation. No, but they agree.
You write the
CPT formula close. CTP, sorry.
Come on, CTP.
Come on, yes, sorry. Okay, so the reflection probability is an expectation value of this form, and so you need to you need to compute this propagation, and this is different for neutrino and antineutrino, and the difference is theta going to minus theta, and integrate over the path. Okay, if you do that, you will see that these are different, and so the source will be proportional to this asymmetry. You need to integrate over the thermal distribution for the neutrino and the antineutrino. Okay, on the momentum space, formula like this, and it's not. I mean, it's not very interesting, but the formula that I get at the end is proportional to the Majorana mass of the descending neutrino, theta over the wall thickness, which is a proxy for theta prime, and okay. And then you have two different behavior dependent on a parameter tau, which is the thermalization scale. Okay, the thermalization scale is set by the interaction of the neutrino with the plasma. So in this model is proportional to this interaction kappa square. Okay. The larger it is, the smaller is the wall. Okay, but since I'm going to discuss some wall thick scenario, I will be mostly in this. Sorry.
How is the thermalization?
Yeah. So is a 10 to the minus 1. So it's a number. So I take the minimum value between these two behavior, depending on the fact that the thermalization scale is large or small. Okay. Okay.
Of what order is the thermalization scale?
Well, the thermalization scale is given by the largest coupling of the descending neutrino to the plasma particle over the temperature. So will be set in this scenario will be set by this interaction. Depends on temperature. Okay, something like that. Okay, so apart from the prefactor that might have different, maybe a different numerical factor, I would say numerical factor in the CPT formulas, we recover these two behavior. Okay, I mean you can explicitly check that setting the width of the particle in the CPT formula is large or small, you recover these two behavior. So I think I trust the scaling. I might not trust the overall coefficient here. Okay, that's an answer.
Why there's a minimum of these two?
Well, because I mean this expression is a bit complicated. So depending on the size of tau as compared to the temperature, I will be in this regime or this regime.
And what does these two regimes correspond to?
Again, so if so I'm in the wall, okay, so I can discuss this reflection transmission probability in a region which is set by t times the velocity of the particle. Okay, so if tau is very large compared to the if 1 over tau is very large compared to the temperature, yeah, mostly, yeah. So there is this regime and there is the regime where they coincide, okay? Which is the thin wall limit. But I will be in this region, okay? So I will get this scaling, okay? Again, this scaling are reproduced with some more refined calculation. I will not bet anything on the prefactor. Okay.
I mean, you have order 1 uncertainty, or is it order 100?
I think the scaling with the parameter is correct, but then there might be some, order 10. Yeah. I mean, these calculations were done just to see if the model was reliable, and eventually it turned out not to be so interesting, so I will not do a more refined calculation for this particular model. Okay, so this is one of the first step to compute the source. Now, since we have the source, we can compute what is the n-number asymmetry as a function of z. Okay. Now, to describe this quantity, we need to solve a diffusion equation. Okay. Which is given by the fact that the current, I can construct a current which is the charge density times, sorry, not times, but with a vector current Jn, which is set by the fact that I'm generating a gradient in n because of the bubble wall. Okay, and usually people discuss this in a diffusion approximation. So this current will be proportional to the gradient in the charge asymmetry times diffusion coefficient, okay, which is proportional to the interaction strength, which set the diffusion of n number. Okay, so scatterings like scattering like this in the region close to the bubble wall. Okay, so I mean the equation that one has to solve is something like this. So you have a time derivative that I trade for a spatial derivative times the velocity minus the diffusion term, which this is just the divergence of the current. Okay, which will be sourced and possibly washed out by the interaction term. So there is a source term, and then there is a washout term of n number. Okay, so there is a term like this, and the rate of washout of n number is very similar to what happens in electroweak baryogenesis, because inside, I mean, you don't distinguish between left and right particles. Okay, electroweak symmetry is broken, and very similar to the estimate in electroweak baryogenesis, this rate is proportional to the ratio of the Majorana neutrino masses over the temperature. Okay, because it's set by the fact that now you have a Majorana mass inside, and you tend to wash out completely the asymmetry in n and n bar, because you don't distinguish anymore between a right-handed neutrino and right-handed neutrino. You have a Majorana particle. Okay, so we can solve this equation. And to solve this equation, maybe it's interesting to realize that there are two competing effects. There is the wall velocity, and there is the diffusion time scale. Okay, so sorry, let me. Sorry. Yes. Sorry? Oh, the density. This is the density of n minus n bar particle. Okay, I'm following this asymmetry. Okay, okay. Now, so there is diffusion. Okay, wow. Okay, so the wall moves. Okay. So I'm defining a region of space which is an effective region where I can convert the n-number asymmetry, which is set by, at equal time you have a diffusion time scale, diffusion length. Let me talk, okay. Let me talk about time scale. You have a diffusion time scale, which is set by d over v squared. Okay, this is a very important scale because I need to be in equilibrium with this interaction on this time scale, because I have only that amount of time to convert my delta n asymmetry in L asymmetry, okay?
Where is then lambda n playing a role there?
Sorry?
Lambda n is relevant for you, correct? And I don't see
Which is lambda?
lambda your
Okay, no, here I'm just following the asymmetry of n. I will compute the asymmetry of n. And then I will process it, okay, on this time scale. Let me write the solution for this equation. Yeah. Yeah. Okay, this is the ratio. Yeah. Okay, so this is the asymmetry that I can transfer to L. Okay, I have this amount of asymmetry in delta n, and I have this amount of time to do something, which is to transfer this asymmetry to L. Okay, notice also that the asymmetry tends to be small, so we are always in this regime because of the washout of a number. Okay. The washout of a number takes place from the wall to the inside. So there is this parameter that is crucial also. Now, I can write the same equation for L outside the bubble wall. And so outside the bubble wall, will be proportional to the asymmetry in n times a factor which is 1 if I'm very efficient. So let me finish. And a ratio of the rate of conversion of a number over that time scale. Okay.
I get a little bit confused. Outside of the bubble wall, the density of the big n should be 0, right?
Well, no, because it diffuses.
Essentially, it washes out.
No, it diffuses. So let me draw a picture for the. You want a picture of this function?
Yeah.
Okay. Okay.
Right.
So this is inside. This is outside. So you have a tail because of the diffusion. Okay.
I thought it's actually the opposite over here.
No, because I think you are confused. This is not again a Baryon number. So the lepton number will be constant inside if I don't wash out. Okay.
No, I think my computing the following. Inside the bubble wall, you will wash out the effect if frozen because of the large mass of the big n.
Which effect?
Huh?
Which effect?
Because of the
Which effect?
So inside your bubble wall, there are no washout because your
Washout of what? So there is washout of n because you don't distinguish n and n bar. There will be no washout eventually of L and L bar. If
no, this is the number density of the big n. Yeah.
okay.
So my understanding that you generated where the source is only inside the bubble wall.
Right, like, well, we already discussed half an hour about this. Like in electroweak baryogenesis, the source of chirality is only localized at the wall.
Yeah.
Okay, fine. Okay, so so this is reminiscent of the fact that this has to be fast on the diffusion time scale. So now the question is,
Recapitulate to the Falun equation.
Huh?
No, the baryon.
yeah. So, but here I'm there, no? Because this is the asymmetry outside. Now I need to take care of the fact that the asymmetry is not washed out inside the bubble, because when the bubble passes through the plasma, I want that they will leave a net asymmetry of L. So now I need to discuss the washout that we are talking about, but it's a different washout.
Oh, sorry, I still didn't get it.
Okay, but then we discuss later. Okay, so now let me draw this picture of the asymmetry in L. The asymmetry in L will follow the exponential suppression of a number outside. And then you want that it goes to a constant inside the bubble, okay? So okay. So to have this effect, you need to ensure that the L number is not washed out inside the bubble. Okay. So now we need to discuss the washout, the possible washout of delta L. Okay. Now the washout of delta L.
Basically, you're saying that the inside of the bubble, they are all converted into the small.
I'm really following electroweak baryogenesis again. Electroweak baryogenesis source an asymmetry in chirality, which is completely washed out inside because SU2 is broken, no? Inside, this quantity goes to 0. Now, you convert the asymmetry between left and right to a baryon asymmetry through the Sphaleron. And then you discuss the possible washout of baryon number, which is avoided by by this very large suppression scale.
It is 0 is simply because that the source itself is 0 inside the bubble.
Source of what?
The source the CP validation source to generate the delta Q is 0 inside the bubble.
So it's washed out, no? It's the same function. It's the same function. I mean, I'm not inventing anything. So this is analog to the difference between left-handed field and right-handed field, the electroweak baryogenesis. Okay. So if you look at plots, people did this very carefully. This they all goes to 0, deep inside the bubble.
Yeah, but I don't think that's the effect from the washout.
No.
Basically, the source is not there.
No, if the source is not there and you don't have washout, you are constant. So this is an equation.
Inside, essentially, it should be frozen into the value of it has at the boundary of the bubble.
Okay, washout of delta L. This is the same story of thermal leptogenesis, okay? Because you have a right-handed neutrino, so you mediate these processes. And like in thermal leptogenesis, the dominant contribution comes when this is on shell. Okay, so now one needs to estimate the rate. Okay, this is done in many papers. And I want to emphasize one thing, which is a common problem also to other models. I'm sorry. I will find the page. But the washout is a potentially very large effect because of the washout is present inside, okay? And also at late time eventually, okay, when the phase transition has finished, while the source only exists at the wall. So potentially you have a large amount of time where you have no source, but you have just washout processes. That's not the case when in thermal leptogenesis. Okay, in thermal leptogenesis you don't have an exponential separation like the one that I'm getting, but it's power law because you have always source and losses at the same time. So what we have to ensure is that these processes are always slower than Hubble for any t after the phase transition. Okay, so this is a very strong requirement that kills the possibility to lower the CISO scale and do something maybe also where you have a phase transition that might be seen in future interferometers. Now the washout rate again is mainly.
So what's the lower bound for this phase transition temperature?
I'm at the CISO scale.
So
So
happens below the CISO scale, so where we wash out by lower bound.
yeah. So the rate is now exponentially sensitive to this ratio. This is the washout rate when you produce a non-shell Rayleigh neutrino, which is the dominant contribution to this process. And you need to compare with what you get in electroweak baryogenesis, which is much nicer. Okay. So this constraint is matched when m over t is order 8 or 9. Okay, so I avoid washout when I'm in this region. Okay, now notice that.
Just a naive question.
Yeah.
So if my M1 over TC is even bigger, is it possible that I can make this mechanism works below the CISO scale?
You know, if a man is even bigger, maybe not even reheat above the phase transition scale. So I mean, even this is pretty dangerous actually.
So did you compute the delta L equals 2, the scattering
Yeah.
processes also? Because they don't get the exponential suppression.
Right, absolutely, and they are not a threat for the delta L asymmetry, which is suppressed by neutrino masses. While here, you are sensitive to both the combinations. Right, when this is off shell, you have no problem usually. Not so much problem. No? Okay, now look at this, and also look at the other formula of the source that I think is this one. Oh, I didn't put the most relevant part. So, in principle, from this distribution, you have an exponent. Okay. So now I have this factor, which will go into the efficiency. This factor that goes into the source. And now I'm really fighting against the E-fold. So I have 23 E-fold for the Baryogenesis symmetry. So it's still okay, but it's very sensitive to this parameter, okay, because you have two exponential terms. And also in the washout, the washout is exponential because I have no source. So this is a potentially very large effect. Now, since I think I more or less chaotically computed everything, I computed the delta L asymmetry, okay, as a function of delta n. I computed the washout rate and the efficiency. I computed everything, I think. I can put all these moving parts together and get the baryon asymmetry as a function of the main parameter of the model. Okay, it's not very important.
So the numbers coming from where?
Well, I mean, basically I'm saying that I'm doing the baryon asymmetry from washout because I'm producing order 1 asymmetry, but then I'm forced to live here, okay? So I'm depleting 1 to e to the minus 8 because I need to avoid washout. Okay, this is a lower bound. To avoid washout at any time after the phase transition, I need to live at this boundary. Okay. So the washout is potentially very efficient, so I need to be a generator order 1 asymmetry to start with. So I'm depleting 1 from an exponential suppression from washout. Okay, so, and the baryon asymmetry is the right number provided that Mn that 10 to the 11 GeV. Okay. The CP violating phase is order 1, order pi. And I'm evaluating the washout and the source at Mn over T equal 8.5, I guess. Okay.
So how big is the initial times together?
Hmm?
How big is this initial times the suppression of the source?
If you put everything together and you put all the numerical factors and the neutrino masses that you have in the model,
It's only 10 to the minus 3?
well, at this scale. Otherwise, it's much bigger. Okay. And notice that since I'm in this regime, everything is proportional to lambda n square, which is in direct correlation with the neutrino masses. Okay. This is the small parameter. Hmm? Okay. And if I don't have this process, I don't generate an asymmetry like the Spaleron rate is factorized in the baryon asymmetry. Now, what we can do with this? Not much, because the phase transition now is occurring at a very high scale. So the frequency peak of a gravitational wave background is 10 to the 5 Hertz, because I think the frequency scales like is linear in the temperature of the phase transition. Maybe this, okay. So very unlucky because we are not into the next upgrade of light. Okay.
The tabletop experiment.
It depends. There are how many? 2 or 3 sources, and okay. Okay, the frequency is mostly set by the phase transition. The abundance is set also by this alpha parameter, which is the ratio of the latent heat released during the phase transition of the radiation, and that is very model dependent.
The small subtlety is that if you have several phases, they added together, then how the V scaled with the V, they may shift a little bit.
Yeah.
You can imagine even both actually the pink of the frequency are proportional to T, but if the two they merge together, but the coefficient in front of them they are not the same, then you get one, which there is a shift.
I mean, there are 3 contributions now, so.
It's always the same order of magnitude.
Yeah.
Yeah, but the several 2, 3 things times together, sometimes they can shift by maybe order of 2 or 3.
Could be. Anyway, so the strain on the strain, but
Which one?
I think this is order 10 to the minus 10, provided that this alpha parameter is order 1, and this alpha parameter is the ratio of the energy released during the phase transition over the energy in radiation. And So maybe it's, I mean, it's very model dependent. I don't know. No, I don't know. Probably not. Okay, so unfortunately that's it, I guess, because the other possible experimental signature depends if this global symmetry is gauge or not. So maybe you can have also a stochastic background of gravitational wave from cosmic strings, but that depends on the fact that you are gauging the B minus L U1 symmetry. You can also have a dark matter candidate in this model, which is the Majoron, because the Majoron at this level is massless. It can get a mass from a Planck suppress operator, and it will contribute to the dark matter abundance via the misalignment production, very much like the axion in QCD.
So the usual bounds on Majorons.
In this model, there are no bounds because the Majoron coupled to only to neutrino, not to electrons. Okay, which is very different. So no, there are models where the Majoron coupled to electron and we have bounds from red giant, even for the CISO scale 10 to the 12. Maybe slightly smaller, but yeah. No, in this model is the Majoron. I think is very. Oh, is a misalignment after the phase transition. So you reheat above the phase transition. You need to average overall the possible initial misalignment angle. And if the Majoron, if the first contribution to the Majoron mass is from this operator, okay, which is the first one you can write. I mean, you can write all dimension 5 operator, but from this one, you get a mass of order 0.1 MeV, sorry, milli-electron volt, okay, which can reproduce the dark matter relic abundance, okay. And the formula depends a bit on the symmetry breaking scale, but I'm putting 10 to the 11 GeV for, let's say, 10 to the 12 GeV for the symmetry breaking scale, and you get, I don't remember the power, but yeah.
Sorry, someone unfamiliar with this graph phenomenology. So then, how is this mass of the Majoron generated?
Okay, so the Majoron mass. The Majoron mass needs to be generated by explicit breaking because the Majoron is a custom boson.
How do you estimate that?
From this?
And Majoron is the phase of this.
Yeah, the Majoron is the phase. I differentiate twice. I put the Vev. Okay, so the mass it will be 1 over VL square times VL. Something like this, so the mass square of the Majoron. Right? The first contribution. And then you put the number and you get around this value. But it's dark matter, you have no chance to see it because it only talks with the neutrino. So, yes?
Jochen just wrote a paper about the...
I was about to ask about whether you can see something in neutrino experiments.
Does the neutrino mass change with time as the Majoron is...
Maybe. I didn't think about that.
So how strong is the coupling of the Majoron to the active neutrino?
Yeah.
Leads to neutrino decay over cosmologically relevant times.
Okay, so the coupling is like for an axion. So the coupling to neutrino is neutrino mass suppress over the symmetry breaking scale. No, I think people call it Majoron J for some reason. So it's this interaction. So it's suppressed.
So the Majoron mass in your case is milli-electron volt. The symmetry breaking scale, let's say, is 2 eV, so that.
Yeah.
11.
Yeah, VL is the Siso scale. Now, unfortunately, if you want to reproduce the baryon asymmetry, you are forced to live at some very high scale. So, no, times a coupling. That's the unfortunate part, in the sense that there was to put the process out of equilibrium. You need to pay a huge price. I don't know, maybe there are better models. I stopped thinking about this, but again, the original motivation was to do something else. Very different, no? But
Good last one.
What's the original motivation?
the original motivation was to, in composite X, maybe at 10 TeV you have a phase transition, stronger first order phase transition. Now, it can couple to some of the standard model particle. How? It's not very motivated, no. You need to couple to... No, I mean, in principle, is a possibility, no? We might be... No, I don't know. No, I mean, why not? I don't know. Maybe there is an abstraction, but...
The transition is large, right?
Huh?
The transition of your original, things and this is very large.
No, but this guy doesn't break...
You might say,
this guy doesn't break any standard model gauge symmetry. It doesn't break SU2. Can only break... Yeah.
It is a thermal contribution from it always exists, right?
It always exists.
And you are talking about 10 to 11. So.
Yeah, it depends on the other parameter. Not really related to this one, because it depends on the ratio of masses of the three neutrinos. So again, this is possibly another contribution. I don't know. This is what it is.
You had two contributions in principle, relax your bounds.
Well, but then,
For very high mass.
yeah. You think it's impossible to do with some I mean, why not? I don't know. Maybe it's impossible. Okay, thank you very much. Sorry.